Chakravarti from Ramakrishna Mission, and he's going to tell us on the possibility of emergent curved momentum space geometry and its impact on deformed dispersion relation in Kappa-Minkowski spacetime.
Hello, I'm audible to everyone? Okay. So, let me begin by thanking the organizers first of all for inviting me and giving me the privilege of speaking here in Ballfest. I had also the privilege of attending the Ballfest 80 in Dublin. So, it is my really, I think I am very fortunate to see him again after 5 years, because we don't get to meet each other very often these days, and I think I'm meeting him after 4 long years. And this talk actually, my student Anisha, who is also one of the collaborators, who is here, gave a talk on this particular topic in 316 seminar of Ball a couple of months back, but it was bit in an incomplete stage. It is still incomplete, but we have made some progress based on some comments made by Bal and Kumar. Actually, TRG and Kumar has extensively worked on this area. So, I think today I'll go try to convince them about these things before and get some feedback so that we can make some final changes and upload the paper in the archive and submit it for publication. So, let me begin by wishing happy birthday to Bal. Probably it is advanced happy birthday. Your birthday I think falls on 22nd or something. 25, okay. Anyway, advance happy birthday to you. So, and this talk actually, let me give you a brief history before I go through the slides. It is almost for 10 years or 12 years that this idea of curved momentum space is floating in the literature, particularly group of people like Glickman and his other collaborators and Smolin, they are working on it. For some reason or the other, I was not very much aware of this kind of activity, particularly I did not take much of notice about its relationship with respect to Kappa-Minkowski space. Somehow it was my fault, I agree. But only recently, maybe 5-6 months back, I went through the paper, I found it absolutely fascinating. Some kind of possibility that can emerge in some regimes of quantum gravity, and it can have deep impact even for the kinematics and dynamics of a single relativistic particle, even if it is spinless, I found it very fascinating. So, at the outset, I must tell you that the Kappa-Minkowski spacetime has different versions, so-called different avatars. And particularly the non-commutative parameter which are introduced, somebody take them to be real constants, as I am doing here. Some people take it to be transforming like a Lorentz 4 vector and things like that. And then some people try to restore the symmetry by deforming the Poincare generators, by retaining the structure of the Poincare algebra intact. Some people deforms even the Poincare algebra, but all the time, of course, ensuring that when the non-commutative parameter goes to 0, then you recover your usual commutative structure. But the beauty of Kappa-Minkowski spacetime, or for that matter in generic Lie algebraic kind of non-commutative structure, is that the structure constant by themselves have the dimension of Planck length. So you can, in the unit of C equal to 1, it will be of the order of root over h bar times g. So if you come down to so-called, in the classical description, you demote the commutator to the level of brackets, call it Dirac brackets, in anticipation that it will be related to some form of constraint structure, constraint form of Lagrangian. So, in that case, the effective non-commutative parameter will have the dimension, will have root over g by h bar structure, and it will have the dimension of mass inverse. So energy scale will automatically emerge even if you require that h bar going to 0 along with g going to 0, but the ratio is held fixed. So the theory automatically, the classical theory automatically get an access into a regime of quantum theory where you are automatically are having an energy scale. This gives rise to the possibility that you are going to end up with some kind of curved momentum space. In this kind of the scenario, that is reminiscent of what happened long back when Gauss discovered the Riemannian geometry. He first discovered the two-dimensional surface with negative curvature, and he found that there is no problem, it is completely consistent theory. And he said that if I can really demonstrate the nature obeys this kind of curvature, means displays this kind of curved surface, then automatically we are going to end up with natural length scale. So if he made a dictum, so to say, I am rephrasing it, the exact wordings I don't recall, that if it is possible to have a non-vanishing value of the deformation parameter having the dimension of length, then it should better have this non-vanishing value. There is almost zero probability that is measured zero actually, that it will be fine-tuned to the value exactly 0. So here also, the moment we have got some mass or energy scale, it is quite expected that the momentum space also will become automatically curved. And this is also reminiscent of what happens in usual special relativity, because the three velocity space, there actually is a curved space, because it is, as you can see, and the addition of velocities if they are non-collinear, they loses their commutativity, and if you consider the addition of three such velocities, it loses their associativity, giving rise to Thomas precision and all sorts of things. So these examples there are plenty of such examples are there in the literature. So here too one expects something like that. So the question is that how do you deal with this curved momentum space and what can be its impact? To understand clearly this impact, one has to, as I have seen in the literature, they emphasize that one needs to study actually the kinematics and dynamics of multi-particle system. Because if you consider collision of two particles and study the addition of momenta, 4 momenta, I just say momenta, and if you find there is a non-linearity, you find that they do not commute, then you infer that the manifold actually is not, means the manifold has a torsion, and if you lose associativity, then you have curvature, and some cases even the metricity condition may be lost. So it is not even a Riemannian manifold, it may be something which transcends that. So keeping all these things in mind, my aim here is something very modest. I'll try to construct rather, a relativistic, Lagrangian of a relativistic particle, spinless relativistic particle, and try to see what kind of impact it can have, the curved momentum space have, on the kinematics through the deformed dispersion relation. So I think that will be good enough for me for 35 minutes talk. So let me begin by flashing the slides one by one. So the classical theory of gravity, as I told you, is expected to be overtaken by some form of quantum gravity, which form we don't know. But one generally desires to have some robust feature which may survive any future theory of quantum gravity. And in this example, if I consider particularly where the h bar and g simultaneously goes to 0, but the ratio is held fixed, then it automatically provides us with a mass scale. And this mass scale ideally should be determined through experiment. Otherwise, I can take it to be arbitrary, but roughly you can think it to the order of the Planck mass scale. And in the context of k-Minkowski space, actually this mass scale is taken to be another invariant quantity, and k-Minkowski space was introduced more than 20 years back by Emil Kamilina and all other people. And curved momentum space, the relationship were also introduced. And particularly an interesting model in 2+1 dimensional gravity, actually when you recast in terms of Poincare gauge symmetry, which being a topological theory when coupled to relativistic particle, point particle, one can show the momentum space indeed becomes curved. Here the Newton's constant has the dimension of the reciprocal of the energy scale. So here you don't have to take any limit or things like that, but in 3+1 dimension you have to take the limit to come to that regime. So these are the some of the references. So my aim is to construct the Lagrangian free relativistic particle moving in Kappa-Minkowski space-time, look for deformations in dispersion relation if any. As a good plausible source, curved momentum space can occur here as I have explained. And my plan of the talk is revisit, I'll start because as I told you, the literature is huge. And we have seen many of the papers, they take different points of views as I have already emphasized. So I'll give you some sample references. These are not exhaustive at all. In fact, the paper which we going to upload very soon in the archive, we hopefully will insert more references. But here as it stands, it is not exhaustive at all. So construction of relativistic particle Lagrangian Kappa-Minkowski space-time invariant under above mentioned symmetry, emergence of curved momentum space and its impact on deformed dispersion relation. This problem of curved momentum space, the metric, as you'll see, it involves a lot of intricacies in the sense that the kind of Kappa-Minkowski space-time I am going to introduce, it involves a scalar deformation parameter. In the sense that the relation 1, x mu x nu, commutator is, I have taken it in the more general form, I a mu x nu minus a nu x mu, or a mu set of 4 real numbers, strictly. So they are just constant, 4 constants. So the commutator with p mu as well as p alpha and m alpha beta vanishes, period. So they are just constant, they don't transform. Nevertheless, here also we can formally write a mu as eta mu nu a nu as a set of new scalars. Just a0 is up or down, doesn't matter, the same. ai down is minus of ai up. That's a set of 4 new scalars. Formally I can still write here, so as if I am raising or lowering indices of 4 vectors. Also I take the magnitude of a0 exceeds that of square root of the sum of the squares of other ai's. That's what is required in the subsequent analysis. And this A, I take it of the order of the Planck length. This algebra as it stands is not stable under Poincare transformation. And to retain the Poincare transformation, one needs to deform the transformation rule. And what we'll do here, we'll take the Lie algebra to be the usual Poincare algebra itself, where we do not touch the Poincare algebra at all. The generators by themselves will undergo deformations in order to preserve that. That will show at the fag end of my talk, albeit classically, but quantum mechanics is a bit difficult. Means up to some operator ordering, it will hold at the quantum level also, that I don't bother. And mu news and p news are the respectively Lorentzian transformation generator. So strategy is the following. We demand that the 2 remains undeformed, deformed infinitesimal ISO 1,3 transformations, ensuring covariance of space-time algebra. Covariance means the commutator algebra is stable under the transformation. Generators and corresponding coproducts are also deformed. These results are already existing in the literature. I'll just mention it for completeness. I'm not going to pursue any multi-particle analysis of any multi-particle system. So I'll just mention it in one of my slides. And so to proceed further, what we do, we consider the action of the Poincare generators on x mu's. And here the action, I take it to be deformed, and these deformation parameters are captured through these 3 objects, psi, phi and chi. So here the parameter a's are occurring. So we require that whenever A tends to 0, these quantities will vanish. In the phi case, it will become 1, and psi and chi become 0 in the limit. So the deformation has to be chosen quite wisely in the sense that we should restore. So we are revisiting this problem. Again, the results are already existing, but they're scattered in the literature various ways. So we have tried to derive it in our own way using the template of this paper, mainly this reference 1, Koch et al. They have done it for the Minkowski's case. So we have, it was a long calculation. I just made a quick revision of this thing, review of the work. So it is an old result, and order of the deformation parameter will try to maintain it at the linear level as possible, because the moment you go beyond linearity, it proliferates like anything uncontrollable, becomes uncontrollable, and we have to, at the end of the day, ensure the proper commutative limit is reproduced. So what we do, make use of the Jacobi identities, where capital G refers to the Poincare generators, M or P, translational Lorentz, homogeneous Lorentz generators. So, Jacobi identities of two types, where X occurs only once, and the second one where X occurs twice. So, you write down the detailed algebra, Jacobi identity, and then carry on this analysis, make certain and such. Admittedly, this and such were, means when we made this and such, symmetry arguments of course helped us, but prior knowledge of the structure was beneficial for us. It was so ultimately we could recover all the results. The details are not required. Finally, what we find is that M mu X nu commutator is given like this. So you can see there is a term where in the 14, 15 there are terms which depends on mu's. So the moment mu goes to 0, you recover the commutative limit. So the important thing is to realize that the P mu X nu relation, there is a factor which multiplies eta mu nu, which is entirely momentum dependent. And this actually opens up the window for interpreting it as some sort of momentum space tetrad that we'll see later. Okay. So the deformed transformation compatible with the spacetime algebra is given like this. You can just apply this commutator and find that deformed transformation is given like this, and deformed Lorentz transformation is also given like this. And clearly the transformations of, they say axes do not transform like vectors anymore. And just I show you the deformed coproduct, which are also, which are basically necessary if I want to discuss multi-particle systems, which I am not going to discuss here. So I skip through this thing, which are available in the literature. So now the task, our main task begins. What we want to do is we want to construct the Lagrangian of a free relativistic particle. So, as I told you, we are not touching the structure of the Poincare algebra. So, Casimir operator remains undeformed. So, unchanged mass shell condition. So, this is the advantage. If you touch the Poincare algebra, if the P mu algebra is not the usual one, then you are a bit difficult situation, because you don't know how to the Casimir, you don't know how the particle classification Ella Wagner will go through. So here you are sure that these things are not touched and they go through as usual. So we want to look for any deformation in the one particle system that I have already mentioned. So we'll try to construct a relativistic one particle model at the classical level. The dynamical model should be such that the action of the Lagrangian should respect the Poincare symmetry. Not only that, even the commutator algebra should also respect the symmetry. This apparently has not been done. Glickman has constructed an action for a relativistic particle, but at the end of the day, only the action part respects the Poincare symmetry, not the algebra part. So stability of the algebra is not ensured. So here, as I told you, we come down to the classical level. So what we do, we demote the commutator to the Dirac bracket, dividing by IH bar and taking H bar going to 0 limit, and introduce this new AMU, which is A mu divided by h bar in the limit h bar and g both going to 0. So this furnishes us with a mass scale in the unit c equal to 1. So these are the Dirac brackets. I am calling it Dirac brackets in anticipation that we are going to identify them as the Dirac bracket of a first order constraint system. So the thing is that usually if you are given Lagrangian, you know to run through the Dirac algorithm, end up with the Dirac brackets. But here the task is opposite. So this makes it a bit non-trivial. We have the Dirac bracket. So from there we can identify what is actually the inverse of the constraint matrix, not the constraint matrix. Then from there the constraint matrix. And from there we have to identify the constraint. And from there we can guess, and after that we can check whether the first order Lagrangian is really yields that kind of Dirac bracket or not. So this is our answer. We write the first order Lagrangian where x and p are the configuration space variable and extended phase configuration space. So pi, there is a pi's for x and pi's for p. So these are extended phase space now. They satisfy usual Poisson bracket, equation 25. And the structure of the constants now, since the first order is usual, given in 26. So this helps us in now if I just relabel the x mu's and p mu's as xi mu 1 and xi mu 2 and recall the definition of the Dirac bracket, you can see that you can obtain the inverse of the constraint matrix as given in 28, and from there again obtain the constraint matrix lambda as given here, where t and c are defined below, equation 29. So from there we have the constraint matrix, and we can, after some guesswork and some hit and trial method, we arrive at the following structure of f mu and g mu, and ultimately the Lagrangian 32. So this is the first order Lagrangian. We have verified it through running backward again, or backward means from this Lagrangian we carried out the constraint analysis. We could reproduce the usual Dirac bracket that we started with. So things are completely consistent. The thing that I have changed here is equation 32. In the last talk that Annesha gave, Ball was unhappy why we changed this first class constraint from p square minus small m square to f of p square minus capital M square. So the answer lies in the argument which is given in the literature already by Glickman, Smolin and all, is that usually when you deal with the flat momentum space, the Casimir p square is regarded as the distance in the momentum space from a distinguished point which is taken to be p mu equal to 0 to some given p mu, and carry out the computation of the straight line distance from the origin to that point p mu. That will give you the distance, and you can identify that as the Casimir. But the moment you say that the momentum space is becoming curved, which I will show now, that you can interpret that way, then you have to replace it appropriately by the geodesic distance coming from the origin to that point P. And the geodesic in general will not be a straight line anymore. Okay. So you can write down the Lagrangian in this way. So E tau is something like a Lagrange multiplier which enforces this modified mass shell condition. This I am of course writing in anticipation, and p square equal to small m square is the eigenvalue of the Casimir, that original one that I had chosen. So my idea is to argue that the small m will be some sort of a quote unquote the bare mass, and capital M will be the renormalized observation, the spirit of quantum field theory. So you see now the Lagrangian I can write down, I can see that if you compare with these flat space Lagrangian, one form so to say, which I have written equation below 33, where you have delta alpha with the Kronecker delta occurring, but here you now have what is shown in here in the blue form, blue color is EP B mu, which is actually this phi inverse P times delta beta mu plus this quantity, whatever is the blue. So you have to have this object inserted here to obtain the first order Lagrangian. And the origin of it stems from the, as I told you, in the original, rather the inverse of it, occurs in the xp bracket, which is the E inverse P B mu. In the bottom, you can see this relation occurs there. Okay. So, this helps us to construct a metric out. So, I interpret it as some sort of a tetrad and construct a metric out of the tetrad in momentum space, and I call it G mu nu tilde eta AB E inverse P A mu E inverse P B mu. Upon simplification, it takes this form. This form is quite nice. It is symmetric under mu nu, everything very nice. But the problem is that forget about diffeomorphism, covariance under diffeomorphism. It is not even covariant under Lorentz transformations, because as I declared at the outset, these A mu's are actually scalars. So the way out is that to make sense out of it, the only way we found is that we say that we take these P mu's to be some, means you have, so all these P mu's are related by Lorentz transformations. So they are referred to some inertial frames you can think of. You choose one of the inertial frame as some reference fiducial frame. And once you have chosen this fiducial frame, subsequent transformations, if any, be it Lorentz transformation more general or more generally any diffeomorphism transformation, require the G mu nu will transform just like a covariant second rank symmetric tensor, as I had shown here in 36. The advantage of this, the d square, the line element, remains invariant under such an arbitrary diffeomorphism in the phase space, in the momentum space, momentum space script P. So, this ultimately I have to show that is independent of the choice of the fiducial frame, and that will turn out to be satisfied. So, let us take this approach, and then I mentioned one interesting thing is that the P mu's they are transforming as vectors under Lorentz transformations, but they don't transform anymore under diffeomorphism transformations. Rather, dP mu's they transform as 4 vectors under this thing. Nevertheless, as it turns out, G mu nu, P nu can be simplified further and given in terms of these things, equation 37. So it becomes, since P square is equal to M square, it turns out to be just a number, and it remains invariant under diffeomorphism also. And it becomes possible because you don't have any term like A dot P. If there are any term of the form A dot P, this would have spoiled its symmetry completely. This is fortuitous for us. So now we calculate the geodesic distance, and geodesic distance is given like this. From the origin, there is a distinguished point to the point P, we have to calculate the distance, and we shall identify the mass shell condition now, modified square of the geodesic distance to the capital M square. And computing the geodesic distance is a very non-trivial job. So what we make use of this differential equation said by the geodesic distance, del mu dp G mu nu P del nu dp. This del mu, their differentiation with respect to in the momentum space, del mu P rather I should write. Anyway, and this is a well-known differential equation, geodesic equation is satisfied, and now we require this C, that means d square, also should be function of P square. This I require because it should also commute with all the Poincare generators, so it should be function of P square. And with this and such, I can really substitute it and obtain 39, and subsequently I can solve it, and after solving it I will get a very nice result. Is a M square is given by this 1 by a sine hyperbolic inverse A times root over P square whole square. So where P square is M square as usual. In A I just written a shorthand of mod A that I introduced earlier. So this gives a relation between AM, capital M and small m. So identify M as a renormalized observed mass in the contrast to the bare mass M. And you can see the diagram is something like this. If you plot the diagram, so what becomes, initially they are almost at 45-degree tangent, but as determined by the scale of mod A, this becomes insensitive after some time. It starts getting, there is no upper bound as such, but the tangent becomes flatter and flatter, so it becomes insensitive to the growth of small m, and this is the feature we observe. And to cast it in the form of usual, because as we said that our space-time remains flat, it is the momentum space which gets curved. 10 minutes, okay, I'll finish it here. Momentum space which gets curved. So what you can do, we can make use of what are called Riemann normal coordinates as defined, introduced at the tangent plane at the origin of p mu equal to 0, and can rewrite this distance square in terms of the normal coordinates. I introduce pi 0 square minus pi vector square is equal to capital M square, and write a relation between pi a and pa. This pa's are the same as the original p mu's actually. I have changed the notation in between when I introduce a tetrad to indicate local Lorentz index and another one for the world index, so to say. And pa by m is nothing but the unit time-like vector, so they can be parameterized as below, as I have shown in the bottom of the slide, unit time-like vector. So you can see that once you cast it in the form of pi 0 square minus pi vector square, this is exactly of the form of what you expect, because this is with respect to the flat metric. Because once you use the Riemann normal coordinate at the origin, the metric becomes flat at the origin, so to say. And everything is described in terms of the tangent plane coordinates. And then it takes precisely of this form. So our claim is that the pi mu's are actually observed for momentum now, and capital M is the observed mass, renormalized mass. I want to use this terminology particularly here in the spirit of quantum field theory. So finally, I just want to pass a remark that I can introduce some sort of coordinate carrying out some non-canonical transformation using this tetrad again, go to this, introduce the q's which are commuting. You can see 45. And using that I can use the deformed Lorentz generators, and these expressions are all the classical level. And you can see that the classical level itself there is a deformation. So Lorentz generators are indeed deformed. Capital P undergoes no transformation, undergoes small p as is shown in equation 44. So the generators are indeed deformed as can be seen in the classical level itself. So finally I conclude, we started by revisiting deformed Poincare symmetry compatible with Kappa deformed algebra in algebraic approach. We also constructed dynamical model for relativistic free particle invariant under deformed symmetries. From these, we could interpret a manifestation of non-trivial momentum space geometry yielding a deformed dispersion relation. The momentum space P in our case cannot be identified as a group manifold. This is a departure from the Glickman side. They identified their momentum space as some sort of a group manifold, part of the de Sitter space, which they call it AN3. But we are not getting anything like that. So the advantage of getting a group manifold is the composition of multiparticle momentum becomes, can be rid of basically from the group multiplication rule, which we cannot do in our case. So all that we have to do is that we have to write down similar multiparticle Lagrangian and then see what is the symmetry and find the generator and study their composition rule. This is the work that we intend to do in future. So it will be non-trivial job, of course. So it becomes a bit difficult to compose individual momentum of multiparticle system to obtain the total momentum. It is therefore quite interesting to see how one can construct a multiparticle action in presence of interactions taken to be simple collisions and study the corresponding Hopf algebra symmetry. So in fact, recently, just last month, this Glickman and Arjano has come up with a paper where they've got good, very well written paper actually, and they actually discussed about the loss. Title of the paper I have forgotten exactly, but the last line says that it is identity crisis, just like the kind of thing that we discussed in the Moyle plane context. So it is more severe there in the Kappa-Minkowski spacetime. So we'd like to look at those aspects more carefully in the future. With this, I thank Bal again.
Thank you, Biswajit. Are there any questions?
Yeah, Kumar, I expected.
First of all, why did you construct the Lagrangian? You don't seem to have used it.
Can you repeat the question in the microphone?
You constructed the Lagrangian, right?
Yeah.
But did you use it anywhere in your analysis?
Yeah. From the Lagrangian itself, I could read off the symmetry generators. I could verify this Lagrangian, enjoy the same symmetry of the Poincare symmetry, and as well as the commutator algebra. The total symmetry is dictated by the symmetry is given by the Poincare generators. Right. So, study the symmetry aspects, I need to study the action in the Lagrangian.
Okay, and the second question is this last reference that you showed, Arzano and Kowalski.
Yeah.
They had some statements about the spin statistics, right?
Yeah.
So, do you have any comment about that in your analysis?
Frankly speaking, I am yet to read this paper carefully. I have just glanced through it very recently, last week. I want to pursue it more carefully in the next few days.
Okay, thank you.
So maybe this is a simple question, but in the initial deformation you wrote in Kappa-Minkowski, could I have not taken the A vector to be null? Like it would still be non-trivial.
That we cannot take. In our analysis, we cannot take. We cannot reach that kind of conclusion. At some point, I have to take it to be, people consider all kind of things. Even I think my Federally Lizzie will be talking about Kappa-Minkowski or some variants of it just immediately after me. He will be talking of all sorts of possibilities. But to get hold of this kind of dispersion relation, I have to take it quote-unquote time-like. Just as if they are vector.
If you just started with the same deformation, x hat mu had a mu and all that, I could have taken A to be null and still non-trivial deformation, right?
Yeah.
Only the mass is not now renormalized, it will be the same mass, but you still have one curved metric, no? Even if A was null?
I don't know. We have not looked into this thing. At certain stage of our calculation, we found that we have to impose this condition. And if we do not impose this condition, it is not clear. We have not investigated it.
Your while being your tetrad, right? Capital A, E, which is function of P.
Yeah,
Means
there are two A's, one for the classical deformation parameter, another is quantum deformation. When I demote from the quantum commutator to the Dirac bracket, so to say, I have to divide by I h bar and take the limit h bar going to 0.
No, I was just saying that the metric.
Metric, okay.
The tetrad E as a function of P, right?
Yeah.
I thought that would be non-trivial even if A was null. I mean, the form of that.
I cannot say offhand. Maybe you are true. I'll check it and let you know.
One small question. The manifold or the momentum space, you said it is not a group manifold.
Yeah.
Is there a way in which you can understand something like a quotient space or coadjoint orbit or any of these things?
Not really.
Because still group theory will be useful.
Yeah, it will be nice to see whether this possibility is there, but I doubt whether this kind of possibility is there here or not. This is a problem actually.
There is no.
Huh?
There is no information about the manifold structure of.
Nothing that I can say beyond this, based on what I have already told at this stage.
Can you find out what are the light cones and what happens to causality?
I have not looked into it, but yeah.
Otherwise, or how do I write the equation for electromagnetism?
Yeah, this is electromagnetic. I have to consider field theory in this kind of space.
But light cones you can do.
Yeah,
right?
light cone I can do.
That will give at least how the light can
Yeah.
possibly propagate.
Yeah.
And so one can ask about causality, and is it something screwed up or is it decent? Because it looks like mixes position and momenta.
You see, our analysis is restricted to massive particle first of all. So what happens to a photon is a bit difficult. the background metric that we see, is, we are claiming the flat, it is actually perceived by so-called zero fold momentum in the limit of p mu going to 0, where g mu nu goes to eta mu nu. But exactly what happens in the case of a photon, that we have to see.
But you can ask what is G mu nu?
Hey, dp mu is equal to 0.
is zero.
That
That will give you the light
means
force.
one expression we had, but for the massive case, I can show you that this expression, equation 37, for example, but it is for p nu, but we have to calculate analogously gp mu, dp nu, and set it equal to 0. That's what you are asking, right?
And you can look at the boundary, and that will give you the light cone.
Okay.
If it is this cones for all mass is an open set, so there is a boundary, and you can take the boundary. You know what the light codes are.
Okay.
Zero, yeah.
Yeah. That may be done, yeah. Good.
Yeah, Professor Lizzie has a question. You can unmute and ask.
My question was exactly the same one that was asked before. What happens if it's not like the vector? And Vishwait already answered. By a coincidence, I wanted to ask the same question as someone else. So
I could not follow.
Saying that he had the same question in mind that Bal asked, so he's okay. He
Okay.
has no new question.
Okay.
what is bothersome is that you cannot hear me.
Yeah, we can hear you, sir.
So if there are no further questions,
Question, can I ask?
why not?
Okay. See, this is a general question, as has been emphasized by Paul and many other people. So classical physics is a probability theory on a commutative algebra, and quantum physics is a probability theory on a non-commutative algebra. So, but here you have both H bar and non-commutativity at the same time. So, can you really distinguish the two?
No, here you see the first case when I started the quantum level, I distinguished between these two non-commutative parameters. Two different A's I used, you remember. One is the curly A, so to say, another is another type A. So in one case, it has got length dimension. Typically, you take it to the order of h bar g. And the second case, when I divide by I h bar and take limit h bar going to 0, then the Planck length actually disappears. Okay, but I simultaneously, so what we will get is something like root over g by h bar. To make it survive, I have to simultaneously demand that the g also goes to 0. Holding the ratio fixed, and this furnishes us with the mass scale, so non-commutativity will be related to the inverse of the mass scale there rather than the length scale.
Now see, my question is a little bit more general. I'm saying if I just look at the algebra of observables and I find it's a non-commutative algebra, can I say whether it is quantum theory or it is a non-commutative geometry? Can I distinguish?
I think you can do it, but the deformation parameter will be just changed. Nothing much will change. No, Sachin, what do you think? Means of course, classically, if you multiply, since only Dirac brackets you are deforming, if you multiply the observables, they will be commuting. they will have commuting sister algebra maybe.
Okay, thank you.
So on this very interesting point, we will unfortunately have to stop, but we will like to thank Biswajit one more time.